Hey there, we're going to work these first two examples for the intro to systems. So number one says we have two boxes. The right box has a mass of 6 kilograms, the left one has a mass of 4 kilograms. They're connected by a string and then pulled by a second string with a force of 60 newtons. So part one, we're going to make a free body diagram of the two boxes. So the first one, we have FG going down, and we'll go ahead and label that Fg is equal to 4 kilograms, or I'm sorry, 40 newtons. The normal force is also 40 newtons. We also have a tension, and we'll just call that T1, okay, and we don't know the magnitude there. The second box, we got a Fg going straight down, and that one is equal to 60 newtons, so our normal force is also equal to 60 newtons. We have a T2 going to the right. That is also 60 newtons. And then we have this T1 here that's connected to that first box. And part B says to write down the magnitudes. We did that. Part C is circle or highlight our force pairs. So that's it. Newton's third law does force pairs. And for this one, it's going to be our T1s. Okay, those are going to be our internal forces there within this system. Now we're going to make our free body diagrams for the bottom box, top box, and then for the two box system. So for our box 1, it's just equal to T1. Box 2, or the top box, I guess that should say the one on the right and the left. It's going to be T2 minus T1. And then to find the net force for the system, remember we just add those for our system of equations. So we have net force on box 1 is equal to T1, net force for box 2, T2 minus T1. So the net force for my system of two objects is going to equal T2. Now that we have that, we're going to apply Newton's second law to our system here, and we're going to find the acceleration of my system. So the acceleration of your system is going to equal the net force on the system divided by the mass of the system. And we found our net force on the system. It was just equal to T2. And then our system is composed of two objects, so the mass of box 1 plus the mass of box 2. Now we can plug in our numbers here. T2 is equal to 60 newtons. The mass of box 1 and box 2, we have 4 kilograms plus 6 kilograms. So we're going to be left with 60 newtons divided by 10 kilograms. So our acceleration here is just going to be 6 meters per second squared. And that's going to be the acceleration of both of these objects here. Now that we have that, we're going to calculate that internal force, that T1, the string connecting the two. And we're going to do that both using the bottom box and the top box to show that it doesn't matter which net force equation we go to solve, we'll get the same answer. So the net force equation for our box 1, remember, was T1. We can apply Newton's second law, so mass of box 1 times the acceleration of box 1. Now we can plug in our numbers. We had 4 kilograms times the acceleration that we just solved for was 6 meters per second squared. So your internal force there, that tension, is just equal to 24 newtons. And we're going to solve for that same force, but now using the information from the box on the right. So the net force on object 2 was equal to T2 minus T1. We'll apply Newton's second law, so mass of box 2 times acceleration of box 2 equals T2 minus T1. We're solving for T1, so we're going to add it to the left and then subtract that into A2 to the right. So your T1 is equal to T2 minus mass of box 2, acceleration of box 2. From here, we can just go ahead and start plugging in our numbers. So we have 60 newtons minus 6 kilograms times 6 meters per second squared. So we're left with 60 minus 36. So our answer here, T1, is equal to 24 newtons. So again, it doesn't matter which net force equation we go to. Once we find that acceleration of our system, we'd get the same answer either way. Generally speaking, you want to go to the one that's easier to work with. In this case, would have been this one here. Now let's go ahead and work another one. This time the boxes are stacked on top of each other. And so we have two boxes. One's mass 6 kilograms, the other one is 4. They're in an elevator. The elevator floor pushes up on that bottom box with a force of 60 newtons. So let's go ahead and draw our free body diagram. For the bottom box, we have the force from the floor, right? It's pushing up on it. And so we'll draw that going up. So this is a force from the floor, and it's equal to 60 newtons. And then we also have our FG going down. And so our FG for the bottom box is going to be 6 kilograms times 10, so it's going to be 60 newtons. So we'll draw that down, 60 newtons. But we also have a force from the top box pushing down on the bottom box. So we're going to draw another one here, and we'll call this, it's a normal force, right? It's a contact force, and it's from the top box on the bottom. So I'll just put T on B. Top box onto the bottom box. Now let's draw one for our top box. So for that one, we have FG going down, and so that one is 4 kilograms times 10, so the weight is 40 newtons, so it should be a little smaller than the one on the bottom. So FG is equal to 40 newtons. And then we also have that contact force, right? So the bottom box is pushing up on the top box, and so we'll draw that going up. And that again is that contact force. This time it's the bottom box on the top. Okay, we have those drawn. Now we're going to circle that force pair. And then that internal force, that force pair here, it's that contact force between those two. Now let's make our net force equations for both the top and bottom box, and then for our system. So the net force on that bottom box is equal to, we have that force from the floor, minus, we have the weight of the bottom box. So I'll put FG bottom so we can distinguish the difference here. Minus that contact force between them, right? The force from the top box onto the bottom box. For our top box, so we'll put net force for the top box. We have the, the normal force, that contact force from the bottom box pushing up on the top one. Minus, we have the weight of that top box. So FG top. All right, so now we can make our net force equation for the system of both boxes. And remember, we just add these two together. And so the net force of my system is going to equal, we have the force from the floor minus the weight of the bottom box minus the weight of the top box. And so what canceled out here was our internal force, right? That normal force between those two, because they're equal and opposite direction there. So we have our net force of our system. Now we can calculate the acceleration of my system. So the acceleration of my system is going to equal the net force of my system, which is the force exerted the floor onto that bottom box, minus the weight of the top box, minus the weight of the bottom box, all over the mass of my system. So M1 plus M2. Now we'll go ahead and plug in all our numbers here. So we have 60 newtons minus 60 newtons, that's the weight of one box, minus the weight of the other box, all over the mass of the two boxes. So we have 60 minus 60, so that's gone, minus 40, so I got negative 40 divided by 10. And so your acceleration is negative 4 meters per second squared, or we can just say 4 meters per second squared down. Now that we have the acceleration of our system, we'll go back to our original net force equations, and we're going to solve for that internal force, that normal force between the two boxes. So we'll rewrite this: net force of the bottom box equals the force exerted from the floor on that bottom box minus the weight of the bottom box minus that internal force that we're solving for. So we're going to rearrange this equation for that normal force, and then so we're going to add that to the left, subtract your net force to the right, and we'll go ahead and apply Newton's second law for the net force and change that to the mass of the bottom box times the acceleration of the bottom box. So now that would give us the normal force that we're solving for is equal to, we have the force of the floor minus the weight minus, now here's our substitution, M2A2. From here we can go ahead and start solving. So the force exerted by the floor was 60 newtons minus the weight of the bottom box, 60 newtons, minus the mass of that box, which is 6 kilograms, times the acceleration, which was negative 4 meters per second squared. So these cancel, and I'm left with negative 6 times negative 4, which is positive 24. So that normal force there from the bottom box to the top box is equal to 24 newtons. Let's solve for the same force here, but now we'll use the top box information. So net force of that top box is equal to that normal force that we're looking for, bottom on top, minus the weight of the top box. We'll add the weight of the top box to the left, subtract the net force to the right, and whenever we do that, we'll go ahead and substitute that MA for our net force as well. So that normal force we're solving for is going to equal the net force. Oops, we'll go ahead and substitute that. So M2A2 plus the weight of that top one. Now we can plug in. So the mass here is 4 kilograms. The acceleration was 4 meters per second squared, negative 4, plus the weight, which is 40 newtons. So I have 4 times negative 4, that's negative 16 newtons plus 40 newtons. So the normal force there is just equal to 24 newtons. So we got the same answer. So your internal force between them, that contact force between these two here, was equal to 24 newtons. The next part here says, how would your answers to E, and E we're calculating the acceleration, change if the positions of the boxes were switched? So we started out with the heavier box on bottom, now we're flipping that. And so the acceleration, remember, was the system is the net force of the system divided by the mass of the system. So acceleration of your system is equal to the net force of your system divided by the mass of your system. And the mass of the system didn't change, right? We still have a 4 kilogram and 6 kilogram box. We just changed their position. The net force of the system, if we look at it, whenever we found our net force of our system here, the force that canceled out was the normal force between them. And that would still happen just when we switch the boxes. So your net force on your system doesn't change either. So since neither one of those changed, then your acceleration does not change either. So it does not change. And then your reasoning here is because the net force on the system and the mass of the system did not change. Then it asked me, how would your answer to F? And in F, that's where we're calculating that internal force. How does that change whenever you switch the boxes? So we started out again with the heavier one on bottom. Okay, so we had this small box here, the 4 kilogram, and then we had the 6 kilogram on bottom, but now we're going to flip it, right? So we're going to put this one on top and this one on bottom. And so what we're looking at is how that internal force would change. And so let's kind of look at this over here, this net force equation at the top box. So if I rewrite that down here, that normal force between them, that's what we're looking at. It was equal to the mass of the top box times the acceleration of the top box plus the weight of the top box. And what we've done now is we have the heavier box on top, so we had an increase in our weight of the top box. The acceleration stayed the same, but now we have the heavier mass box on top, so we have an increase on this net force here. So that means that this internal force has to increase. Okay, so the internal force there would increase because in this situation, your larger mass will be applying a larger normal force to that smaller bottom box. So again, whenever you're solving these problems, start out with your free body diagrams of both objects. Find your net force of your system. Apply Newton's second law to the system to get the acceleration. Excuse me. And then you can go back to your original net force equations and then solve for that internal force on the system.